Okay, the final exam, guys, will be on the 18th of November at 4:30 p.m. and the exam will be for 3 hours. And as you know, the exam will be mostly or all the exam will be calculation based exam, and the exam will be online. So you will need to download or work on the exam using your screen and then solve the exam in with handwritten papers and then scan your solution and then upload again to the system. Okay? Have you had online exam before, guys? Any of you? I will post the exam instruction next week so that you have also idea what you need to do and how to upload because you need to give some time for the scanning, maybe 5 minutes at the end to scan and upload the solution to the system. Okay. Do you have any question, guys, for me in this course? In the class today, I will solve one or two examples. Okay. Do you have question, Ifan? Can you tell me what is your question or what is your problem with the course? No. Okay, guys. So I will now start sharing the slides so that we can go through the slides. So as you know, this course we have studied two parts or two topics, two main topics. The first topic was designing of hot rolled steel sections. So we have hot rolled steel. This was the first half of the course. Thanks, Sifan. And hot rolled and cold formed steel design. And this is the requirements for the course. We have gone through all the requirements. The outline for this slides are the general design principle in steel design, second order effects in steel, design of hot rolled members, and design of cold rolled steel member or cold formed steel members. And here is quickly what are the general design principle for steel. We have stability limit states for whole or part of the structure to prevent the instability due to overturning or uplift or slidings. Strength limit state or ultimate limit state. The ultimate limit state are for component or members or connection capacities. The capacity should be larger than the loading effect, which means that applied load or M asterisk N asterisk V asterisk should be less than or equal to the capacity. The capacity which is phi ms or phi mb or phi ns, phi nc, phi vv. All these are the capacities of the member. So the applied load should be less than or equal to the capacities. The third design principle is the serviceability limit states, which controlling the or limiting the deflection, vibration of beams, draft, or any sort of deformation. So in this case, we should limit the deflection or deformation to be less than or equal to delta allowable or the allowable limits. The allowable limits, which are span over a number, which is, for example, 300 or L over 400 based on the member. These allowable limits can be found in AS 1170.0 or the relevant standard AS 4100 or AS 4600. 4100 for hot rolled and for cold format AS 4600. The strength limit state, again, as you see here, phi RU is more than S asterisk or the strength or the capacity more than the applied load. Where phi is what? Appropriate capacity factor. Okay, so phi is the appropriate capacity factor for each case. So based on the design case, you can find the relevant phi. For hot rolled steel, phi equal to 0.9, and for cold formed steel, phi can be 0.85 for compression member, zero point 0.9 or 0.95 for tension, bending, shear for members. Okay, so we have different phi for hot rolled for all members, zero point 0.9, and phi has different values for cold formed, 0.85 or zero point 0.9, 0.95. So based on the design case for cold format. Okay, so these are the general rule for strength capacity or strength limit state design. One of the important topic in our design is the second order effects. The second order effects are included in both hot rolled and cold format steel design for members under moment and normal force. So the second order effects for member under combined axial compression and bending. May I ask you which member you expect will be under combined axial compression and bending moment? Do you know or do you have idea? What are the members that are under combined actions from your design? Yes, column, frame column. Thank you, Michael. So the frame columns are the main members that has or that under axial compression and bend. For this type of design, the buckling will affect the moment because what is the problem with compression buckling? So buckling will affect the design for moment. So that's why we need to consider the second order effects, which will be by using the amplification method. The amplification method means we increase the maximum moment on the member. So in second order effects, we need to consider the buckling due to axial compression. How to consider the buckling due to axial compression? Using increasing M max. So this is how to consider it. Okay. Another thing is also the deflection or the lateral displacement will be affected as well. But our focus on what? MMX. For the hot rolled steel, AS 4100, the second order moment MMX may be calculated through a moment amplification factor, and this will be using separate calculation. For cold formed steel, usually subjected to small compression, B delta included effect in the equation. So what this mean? The second order effect for hot rolled steel need to be considered or calculated separately. But for cold formed, it is included in the calculation sometimes. Okay, or let's keep it like this now. So the main thing is for second order effect should be considered to consider what again? Buckling problem due to axial compression. Okay. And this is a reminder of the moment amplification factor for braced member in what? From AS 4100. So this one for hot rolled steel member. So the moment amplification factor for braced member is delta P. So our moment is M asterisk, but our desired moment will be M asterisk equal to delta B. So delta B is the amplification factor for our moment. How to find the amplification factor from from the standard 4100? So delta B equal to a factor of Cm divided by 1 minus N asterisk over NOMB. And delta B should be more than or equal to 1 because it is increasing factor, so it cannot be less than 1. So NOMB is elastic buckling load determined in accordance with clause 6.462. Do you know the formula for this one? Or what is NOMB? Do you remember? I will just open the standard with you so we can have a look on it. So NOMB is the elastic buckling load or Euler load, and it can be found using clause for 4.6.2. Okay, guys, can you see the standard now? So here is the factor or the member axial, the elastic buckling load. Can you see it? Yes, thank you. So here is our NOMB. So it is the buckling load by squared EI divided by KE times L all squared. If you are calculating NOMX, so buckling about X, this will be IX, and this will be K effective LX or LEX. Okay, so this is our NOMB, which is Euler buckling load. So we know NOMB, we know N asterisk CM. CM for braced member subjected to independent moments only. The factor Cm shall be calculated as the following. So Cm equal to 0.6 minus 0.4 beta m less than or equal to 1. So this is a factor affect or considering the end moments of the member, where beta m is the ratio of the smaller to largest bending moment at the end of the member. So if you have a look here, if this our column or our member, so this member under two moments, for example, so we have one of them M1 and other one is M2. So actually Cm is the value of M1 to M2, where M1 is the smallest moment, M2 is what? The largest moment. Okay? But there is two signs for Cm. Can be negative or positive. Who can tell me when it is negative, when it is positive? If you go back, so taken as positive when the member is bent in reverse curvature. So Cm is positive when we have reverse curvature like this one here. So the moment here, something like this. So actually, this is how the moment will bend. We call this reverse or double curvature. So double curvature, positive. Single curvature, negative. Okay? So this positive, this negative, and this positive for Cm. Sorry, this for beta, not for Cm. So this is beta m. Because Cm is already 0.6 minus 0.4 beta m. So beta m is the ratio of m1 to m2, can be positive or negative. Positive if the two moments creating reverse curvature like that, or negative if the two moments creating single curvature like that. For sway member, so the first one was for raised member. For sway member, the moment amplification factor for a sway member is called delta M. So delta M for sway member. The moment amplification factor for a sway member will be the greater of delta B calculated from raised member calculation, the previous slide, and delta S. So actually delta M is the least of, or sorry, the greater of delta B and delta S. Okay, where delta S is equal to 1 divided by 1 minus 1 over delta MS, where delta MS is the is the elastic buckling load factor for story under consideration and determined using clause 4.7.2.2. from the formula here. So delta ms is the elastic buckling load, and delta ms is equal to summation NOMS divided by L divided by summation N asterisk divided by L. Where, what is NOMS again? NOMS is again elastic buckling load, which is pi squared EI divided by L effective squared. Okay, so if we have more than one column, so we need to find the summation of the buckling load for each column divided by the length of this column divided by summation n asterisk for all columns divided by the length of all columns. Okay, so this is the implication factor for sway member and brace member. And one more thing for the columns or frame columns especially is what the buckling length LE. LE is equal to KE multiplied by L, where KE is what? Buckling length factor or effective length factor. Where does this buckling length factor come from? If we go back to our standard, so here is the buckling length factor, close 4.6.2.3 and close 0.4.6.33. So these two closes will give us the factor Ke. Actually, we have two cases for, or two methods for calculating Ke. One of them is, as you can see here, is what? Idealized end restraint. Idealized end restraints is for theoretical calculation or for simplified calculation. So for simplified calculation, we have two cases, braced columns or what? Sway columns. As you can see, for braced columns, Ke or the effective buckling length Ke is less than or equal to 1. So it is 0.7 for fixed, 0.85 for bin fixed, and 1 for bin. So for braced member, Ke will be less than or equal to 1, and the ideal supports are fixed, bend, or fixed, bend, fixed, and bend. For sway member, Ke more than or equal to 1.2. So here less than or equal to 1, here more than 1.2. So if the member, sway member, we have fixed at the bottom and rotation fixed, translation free at the top, because any sway member means the member can move laterally, delta or draft. So the first case, fixed with rotation fixed and translation free, is 1.2. If it is fixed free, so 2.2. If it is bend and rotation fixed and translation free, 2.2. Okay? But this only can be used for ideal calculation or simplified calculation. And for frame members, clause 3, 4.6.3.3, we are using close for we are using it for members in frame or column or frame columns. Okay, so for frame columns, we are using this method here. Actually, this method we have this chart for braced members. So any plot in this diagram or this figure is a value of what? KE. So KE will be found using this table for braced member and sorry this figure for this for braced member and this figure for what? For sway member. And as you can see as well here, KE for sway member is more than 1.05 or more than 1 in general. Here for breast, KE is less than 1 in general. Okay, but the idea is how to find KE. So we need to have these two values, alpha 1 and alpha 2, to find the value of KE using this chart or this figure. Okay, how can we find alpha 1 and alpha 2? Using this formula here. Sorry, gamma 1 and gamma 2. How can we find gamma 1 and gamma 2? Gamma 1 and gamma 2 will be using this clause here. Okay, so this is where to find it in the standard. If we go back to our slides again quickly. So here is our chart. Can you see the slides? Yes. Okay, so here we need gamma 1 and gamma 2. And here also need gamma 1 to gamma 2 for sway members. This was for braced members. So the stiffness ratio at ends or gamma will be found using this clause here. Gamma equal to summation I over L for column divided by summation beta E I over L for beam. Okay, so if you have a column, just quickly here, connected to a beam in a frame or rafter. This is our rafter and this is our column. So we need to find gamma 1 and gamma 2. Okay, gamma 1 is a relation between rafter and column. So this is where we can use this formula here. But if you read these two statement here or these two conditions for compression member whose base is not rigidly connected to a footing, gamma shall be taken as 10. So for not rigidly connected means for bend base or bend support. For compression member whose end is rigidly connected means fixed base. Gamma is equal to 0.6. So what this mean? Gamma here in this case will be 0.6 because this case is fixed. If we consider hinged support on the other column here or bend support, so this one is bent. How much is gamma 2? 10. So here at the top here, we have gamma equal to I over L for column because we have only one column here divided by beta E multiplied by I over L for the beam. So if you know I for the column, L for the column, it's okay. I for the beam, L of the beam. So you know I and L for beam. We know this information already. We know I and L for column. So we know this information already. So what is missing or what we need to find now? Beta E. Beta E is using table 4.6.3.4. So what does this mean? We have the fixity. This is the values of beta E, one of these six values for sway member or braised member. So if we consider this frame, this frame is what? Sway frame. Because no thing prevent this frame from from lateral movement. Actually, this frame can move laterally. So if the frame can move laterally, so this is what? Sway frame. This lateral movement is delta or draft. Okay, so if this a sway member, we need to look at the fixity condition of the far beam. So if the end of the far beam bent or fixed or rigidly connected to a column. So actually in this case, where is the far end of the beam? Here is the far end of the beam. So actually this is our far end of beam. So the far end of the beam can be fixed or hinged or what? Connected to a column. So if it is connected to a column, beta effective in this case will be 1. So as you can see here, rigidly connected to a column, so beta is 1. Okay, so if we know beta as well, we can find gamma. If we know gamma 1 and gamma 2, we can know what with gamma 1 and gamma 2, we can find K effect. Okay, so this is the exact calculation or the detailed calculation for finding K effective for columns of frames. Do you have any question, guys, up to here? No? Okay. Now let's go through. Do you want a rest now? Do you want some rest or we can continue? No answer? Okay. Thanks, Michael. Thank you for confirming. So now let's have a look on or remind ourselves with the design of hot rolled steel member using AS 4100. So for design of tension member, this is covered in section 7 of the standard. So design for axial tension, no buckling problem. So that's why or no buckling issue. So that's why but design of tension member is straightforward and not much calculation, not many calculation. So we have n asterisk should be less than phi nt, where phi from table 3.4 for all hot rolled steel member, phi equal to 0.9. NT is the nominal section capacity according to section 7.2. So if we go to section 7.2, nominal section capacity for tension, actually NT is two values. Okay, so NT will be the lesser of two. One of them for the gross section area, one of them for the net area. If you remember, the gross section area, this for yielding failure, and the other one for what? For rupture failure. Okay, so if you know a gross, F yield, KT is the correction factor for distribution of forces determined accordance with clause 7.3. AN is the net area, so means A gross minus area of bolts hole or bolt holes. Fu is the tensile strength. So F yield strength, A gross section area, Fu is the tensile strength. The value of KT is using this table here based on the members we are designing. Okay, so if we have plate connected to an angle, so KT will be 0.7 or 0.85. So 0.75 for unequal angles connected to by the short leg. If it's connected by the long leg, so it can be 0.85. This one, we have two angles with a plate, similar to case A. If we have C section connected to a plate, so 0.85. If we have T section connected to a plate, we have 0.9. If we have two angles in two different cases, so the distribution factor will be 1. So this is just a factor to correct or for correction due to the how the stresses are distributed between the members. So this is the design of tension member. And next is what? Design of member under axial compression. This is covered in section 6. So section 6 of the standard will cover the compression member. And again, the problem of compression members are buckling issues. So we have two buckling problems. One of them is local buckling. So we have local buckling problem and global or overall buckling problem. So in the design of axial compression member, we will consider the local buckling in the section capacity calculation, and we will consider the overall buckling in what? In the member capacity calculation. So in the design of cold formed steel members, in the design of hot rolled steel members under axial compression, we should satisfy two conditions. N asterisk should be less than the section capacity phi ns, and N asterisk should be less than the member capacity phi nc, where phi for both cases are 0.9 because it is 0.9 for all hot rolled members. Okay, so now how to find ns and how to find nc. For ns, it is equal to kf multiplied by an times f yield. where AN is the net area as before, F yield strength as before, and KF is shape factor using this formula. So KF is the shape factor using the formula AE divided by A gross. A gross is the whole section area or the gross section area, and AE is the effective section area. So AE is the area that consider or local buckling, considering local buckling, because after our course, you know now that when the section under compression, parts of the section are not actually working due to local buckling. So this is considered in the A effective calculation. The effective the effective area calculation will be calculated from the gross area by summing the effective areas of individual elements whose effective weights are specified in clause 6.2.4. So to find A effective, we will need to find B effective for the cross-section element, like web, flange, and so on. Okay, where B effective equal to B multiplied by delta E yield over delta E, where delta effective is the cylinderness ratio. Sorry, lambda E is cylinderness ratio multiplied by equal to B over T root F field divided by 250. So this is our steps of finding B effective. We need to find lambda effective first, and then find B effective equal to lambda EY divided by E yield. And here is the values of the yield cylinderness limits, because the yield strength, the cylinderness limits will help us to find what be effective. So be effective, we need lambda EY or lambda effective yield. So using table 6.2.4, we can find this lambda. So for members, blade element type flat, if it is supported from one end, this means for flange. Because flange is supported from only one end, the other end is free. And both for what? For web, because the web is supported by here and here. So this one for web. So based on the type of the residual stresses, we have SR, stress relieved, hot rolled, cold formed, LW. Do you know what is LW? LW and HW, light welded or heavy welded. So in your project, if you remember, if you use welded beam, so you will use phi lambda EY as 14 for flange and 35, sorry, yeah, 35 for web, for example. Okay, so this is how to find lambda EY, and the table 6.2.4 give us that. And the next part is how to find the member capacity in C. So the member capacity in C is a relation of or a function of ns. So the member capacity is a factor alpha c times the section capacity ns and should be less than or equal to ns. So how to find n lambda alpha c? Ns already from the previous calculation. So how to find gamma c? Gamma c is the member slenderness reduction factor to account for or considering what? Overall buckling. So to consider the overall buckling, we need lambda alpha c. So alpha c, if we go back to the standard to have a look on it in the standard. So what section covering the member under compression, axial compression? 6, section 6. So here is the section capacity. Here is the form factor. Here is the slenderness ratio, delta lambda e. And here is the effective width, BE equal to B times lambda EY over lambda E. And here is the table for, here is the table for the slenderness limit lambda EY. For the section, for the member capacity, section 6.3. So here NC equal to lambda C NS, where lambda C can be found using this formula here, zeta 1 minus root and so on. And we need lambda equal to lambda n plus alpha A alpha B, and lambda n equal to LE over R root KF F field over 250. Alternatively, we can the values of the member slenderness reduction factor may be obtained directly from table 6.3.3c using the modified member slenderness lambda n. Okay, so the formulas for or the detailed formulas for the lambda c is here, but maybe taking effort or lengthy calculation. So the standard give us another option to use table A 6.33a, B, and C. So if we look to table 6.33c for the factor lambda c, we need two parameters. One of them is lambda n, one of them is alpha b. Lambda n is the modified slenderness or the modified member slenderness using this formula here. So here is lambda n. And what else? Alpha b. Where is alpha b? Alpha b from table 6.3a and b. 6.33a for values of kf or the form factor 1, and 6.33b for form factor less than 1. Okay, so if we go back to our slides, so we will directly consider what we need to find alpha c. Two things. One of them, or the important one, is lambda n. The other parameter is alpha b. So this number 1, this number 2. For lambda n, it is equal to L effective over R multiplied by root KF multiplied by root F yield over 250, where L effective is equal to KE times L, where KE is the buckling coefficient we studied or we discussed earlier, buckling length factor. And Kf is the form factor equal to AE over AG from the previous calculation here. KF equal to AE over AG. Okay, so if we go back to the standard here, if we know lambda n and we know the shape factor kf, the form factor kf. So for example, if kf less than 1 and we have the section, for example, is hot rolled UB section, flange up to 40. So how much alpha b? 0. So if alpha b 0, we can go to this table, assuming that, for example, lambda n is equal to 20. So at 20 and alpha b 0, so our alpha c is this value. So alpha c equal to 0.978, so that we can find we can find the member capacity in C. Okay, guys, do you have any question now? So another type of columns, or one of the types of the columns, is the built-up columns. The built-up columns, we have two types: laced columns or buttoned columns. So laced column like this one here, buttoned column like this one here. So laced column is members like the vertical members here, and connected together with small members working as truss elements. This is the main difference between laced column and buttoned column. So for laced column, the diagonal members working as truss elements, and that's why they are diagonal members. But for buttoned column, we have also, this is the main members for us, or the vertical members like channel or angle or angles and so on, but connected together with buttons or buttons. These buttons are not truss elements, they are working like frame elements. That's why they are horizontal member. And that's why also the size of the buttons are large compared to the diagonals here. So truss elements means, what you understand when I told you truss element? Truss element means this member can carry only axial loads. So this is a main characteristic of the truss elements. For frame elements, this means it can carry what? Shear and moments. Okay? So this is example of laced column, and this is the shape for buttoned column. Okay, do you have any question for the two columns? Have you designed the laced column in the project? So for design of buttoned column and laced column, we have two main design criteria. The first one, or the main one, is the cylinderness for the members or the component of the member. So we have cylinderness ratio of the main component. The main component is actually, again, as I told you here, We have actually what two main component like two channel or something like this. So these are our main components of the list column or buttoned column. Okay, for example, two channels. Then to make them working together, what we should do, we connect them with what? Some diagonal members like that. Okay, so if we connect them with small member or truss element like this, so this is what laced example of laced column. So actually, these are our main component because these are what is carrying the load. Okay, but this member are working to connect them together to work as one member. Because if the two channels are not working together, we don't benefit from the additional strength coming from working together. So we have some checks for the cylinderness of the main members or main components and the buttoned compression member. And another check will be for buttoned column, we need to check the shear and the moment on this buttoned member. So we have two design criteria. One of them is the slenderness ratio. We need to make sure that this members will not or this components will not buckle. Another thing is we need to check that this buttoned member connecting the two vertical members or the two main components. This member is our button is strong enough to resist the shear and moment come from the column. Okay. Do you have any question for the button and list column? Nothing? Okay, can we have a 5 minute break before going to the flexion member? So we meet at 10:25. Is that okay? You guys, can we resume now? Okay, so the next member to design or the next uh the next string action we need to design is flexion members. So flexion members are covered under section 5 in the Australian Standard 4100. Again, flexion members will be subjected to some compressive stresses. So the compressive stresses will cause what? Buckling issue. So we have buckling issue as again in flexion member. That's why we have to satisfy or calculate section moment capacity considering the local buckling issues. and member moment capacity considering the overall buckling issue. So that's why m asterisk x should be less than or equal to phi m s x and phi m b x. Again, if we have our cross section, I section or UB section, so this is generally x axis. So the moment is working like that. So this moment causes tension in this part and compression in the top part. So that's why we have a problem here. Compressive member, compressive stresses. Okay, so this for the compressive stresses. So we need to satisfy these two conditions. Again, phi for this case is 0.9. Mx asterisk is the applied moment from the applied load. Msx nominal section capacity, Mbx member capacity about x-axis. So how? Firstly, to find the section moment capacity or Ms. So the nominal section capacity Ms is equal to F yield multiplied by Z effective, where Z effective is the effective section modulus. Okay, so ZE is the effective section modulus and shall be calculated using clause 5.23, 5.24, and so on according to the appropriate section, appropriate case. So to find ZE, we need to know the slenderness ratio first. So just quick here. ZE has different cases because we have compact section, non-compact section, and slenderness or cylinder section. So that's why we need to know the slenderness ratio to know which case to find. So we have compact, non-compact, and cylinder. So how to know which case to use? We need the section slenderness. The section slenderness is lambda E. So lambda E is equal to B over T multiplied by root F yield by 250. Okay. Then we need to compare this to, first we need to find this for all the elements or the component of the member. So we have for flange and for what? For web. Okay. And then we need to compare it to the limits. We have plate yield strength limit and plastic strength limit or plastic cylinderness limit. So we have plate yield strength limit and plastic cylinderness limit. B is the member width or the clear member width. T is the member thickness or the element thickness. And here is the element or the limits of the cylinderness lambda. So we have two limits to use in our calculation, lambda EY and lambda EB. Lambda EY is the yield limit. Lambda EB is the plastic limit. So we will need to know if we are calculating for flange or web. So these two for what? For flange, and these two for web. Because flange is supported from one end, web supported from both ends. And also we need to know the distribution of the stress, uniform or compression at one edge and tension on the other. So here we have compression one edge, tension on the other. Here we have uniformly compression. Here we have uniformly compression as well. Here we may have something like this or something like this. Okay, so based on the case, flange or web, the type of stress and the residual stress, so you can find the limits lambda EB and lambda EY. Then how to decide it is compact or non-compact or cylinderness. So using lambda for the section, okay, which is you see here, lambda S is the greatest value. So lambda S is the greatest value for lambda E for whip and lambda E for flange. Okay, but after dividing by lambda E Y. So lambda S will be the critical lambda from the web and the flange. And according to that, we will know if it is plastic, sorry, if it is compact section, non-compact section, or cylinder section. When the section is compact, when lambda S less than or equal to lambda S plastic. When it is cylinder, when lambda S more than lambda S yield. So actually here, if we look to any example, for example, let's assume here, if lambda less than, if we are calculating for this part, for example, if lambda less than 82, this is compact. If lambda more than 115, so this is cylinder. So this means when the lambda value go up, this means the section is likely cylinder. When it is go down, this means that the member is likely compact. The non-compact section is a case between compact and non-compact. So this happens when lambda is more than SCB and less than S yield. So in between, it will be non-compact section. For compact section, Z effective is the lesser of S and 1.5 Z. So here, Z effective is equal to the smaller of two values, S or 1.5 Z. These two coming from the tables, the members capacity table, where Z is the section modulus and S is the plastic section modulus. For cylinder member, for cylinder member, Z effective equal to Z multiplied by lambda SY divided by lambda S, where Z is Z from where? From tables. The middle case or the non-compact case is interpolation. So here Z effective equal to Z plus psi S lambda S yield minus lambda S divided by lambda S yield minus lambda SP multiplied by ZC minus Z. Where ZC is the effective section modulus for a compact section specified in clause 5.23. So ZC here is one of these two values according to the lesser of these two. So actually, this value coming from interpolation between compact and non-compact. Okay, so according to whatever the value of lambda and lambda s and lambda b, you can find the value of ze. If you know ze, you now can find ms. Okay, and the next step is what? Member capacity. For the member capacity, we have, let's put it here, the member capacity. We need to include what or consider the overall buckling behavior of the member. So the overall buckling behavior will be controlled or decided by the compression flange, because our compression flange is the critical flange. So actually the overall buckling behavior will be according to the compressive flange. So we may have continuous restraint. Continuous restraint means if we have a slab or shaker plate or timber floor, so this means that the compression flange or the compressive flange will be prevented from buckling. So actually the factors or the calculation will be based on the compression flange restraints. So the first case is segments without full lateral restraints for the compressive flange. So the formula or the equation for lambda for MB or the member capacity is alpha M alpha S ms. So MB x equal to alpha M alpha S msx and should be less than or equal to msx. So we know msx already, so we need these two parameters. Alpha M is the moment modification factor, alpha S is the slenderness reduction factor. So here we have two options again. We can find alpha M and alpha S alone, like separately, or we can find the two factor as one block. So alpha M using the formula 1.7 mm asterisk divided by root m2 asterisk m3 asterisk m4 asterisk and should be less than or equal to 2.5, where mm is the maximum bending moment in the segment. So if we have a simple beam, for example, and we have this moment, so this is our maximum moment m asterisk. M2 and M4 are the determined bending moment at quarter points of the segment. So if this our segments L, so we have L over 4, L over 4, L over 4, L over 4. So this one of them is M2, one of them is M4. M3 is the desired bending moment at midpoint of the segment. So actually here M equal to M3. So this is an example of this factor alpha M. Okay, so this is the factor alpha m. Another factor, which is what? Alpha s. The other factor is alpha s. So the slenderness reduction factor alpha s is using this formula m.6 ms MOA and plus 3 minus ms over MOA. So we know ms. So what is missing or what we need to find now is MOA. MOA is equal to MO, which is the reference buckling moment. So MO is the moment, the buckling moment, or the moment when the beam will start buckling. The moment when the beam initiate buckling. Okay, MO is using this formula here. Okay, MO will be using this formula here equal to, sorry, the screen freeze. Sorry guys, just a second. You guys, can you see the screen now? So MO is equal to this formula here. By squared EIY and divided by L effective squared plus GJ by plus by squared EIW divided by L effective squared, where, as you know, E is Young's modulus, 2 times 10 to the power 5 MPa. G is the shear modulus, 80 times 10 to the power 3 MPa. J is the polar moment of inertia. IW is the warping inertia or the warping elements. L effective is the effective length determined in accordance with 5.3.6.3. Okay, just note here, this is currently MOX. So that's why if this MOX, this is what? IY. Okay, so the parameter we need to calculate now is L effective. So L effective is the effective length of the member equal to KT, KL, KR times L. L is the segment length or the beam length. So the factor KT is from table 5.31 here, based on the restraint of the two ends. So if the two restraints is fully restrained or partially restrained or lateral restrained, so we have F case F or L lateral restrained or U unrestrained. So based on the case, this is a vector of KT according with the end restraints of the two ends. So we have end number one, end two. So we need to know if it is fully restrained or lateral restrained or partially restrained or unrestrained. For the factor KL is load height factor for gravity loads, table 5.6. So this will give us where where the load applied to the section. So if the load within the segment, the restraint arrangement one of these, and if the load is added to the shear center or top flange, because for a member like an angle section, for angle section for BFC channel, so the load can be applied to the top flange or can be applied at, if this is our x-axis, so this is our shear center, so the load can be applied here to the shear center. So this will affect our factor KL. So usually loads are at the top flange in our beam design, so it will be one of these values. The third factor, sorry, is KR. KR is the lateral rotational restraint factor, which means if we are preventing the rotation or lateral rotation of the member or not. So this table 5.6.3. So based on the restraint again, one of these cases, and if you have support at any or none or one of them or both, so this will be our factor KR. So the last one, if you have lateral restraints, or sorry, not lateral restraint, rotational restraints at the two ends, end one and end two, for fully restrained case, so the factor is 0.7. So if you know the three factor, you can know what L effective. Okay. So after getting L effective and using the section probabilities and material probabilities, you can easily find MO. If you know MO, you and ms, you can find alpha s. And if you know alpha s and alpha m, you can find mb. Using mb and ms, you can find, or you can design the member for member capacity here. Okay, and using mb and ms, you will design the member or the flexion member under bending moment. Okay, to satisfy these two conditions here. What other design requirement for flexion member? For flexion member, another requirement is web design or design of member for shearing capacity or bearing capacity. So for flexion member, we have design for flexure or bending moment, which we have done already. Number two is shear capacity. Number three is bearing capacity. So for web design or for shear capacity and bearing capacity, we may have what, as you can see here in this diagram, we may have transverse stiffeners and what, longitudinal stiffeners. These stiffeners will strengthen what, the web, and they will increase their shear capacity and member capacity. So for shearing capacity for unstiffened web, so you need to make sure what is the design requirement or what is the case of you are designing. If you are designing a stiffened element different from unstiffened element, so the shearing capacity is satisfying this formula. V asterisk should be less than phi VU, where V asterisk is the design shear force, phi again 0.9, VU is the nominal section capacity in bearing. The nominal section capacity in bearing will be depending on this ratio here. So D, we need to compare dB over TW and compare to what? 82, 82 root F F field over 250. So if less than this factor, this means that the web is stocky web. So this means the buckling will be yield. We will reach the yielding buckling capacity. So in this case, V equal to V W. This is the maximum shear capacity we can reach. 0.6 F yield area web, where area web is D web times T web, or dB times T web. Okay. The other option, if this ratio dB over TW more than 82 root F yield over 250, we will not reach yield because buckling will happen. In this case, buckling occur, shear buckling occur. Here, yielding occur. So here, VU equal to VB equal to 82 divided by dB over TW multiplied by root F field over 250. All of this square multiplied by VW. Okay, so this is the shear buckling. Just to quickly have a look on this formula on the standard. So this part is covered in this clause here. Design of member subjected to bending. So we have shear capacity of web. Okay, so this is the formula for V equal to VW when dB over TW less than this formula here. Okay, and VB equal to alpha V VW, where alpha V is equal to this this ratio here, 82 divided by dB TW root F yield over 250 all square. Okay, so again, if we go back again to so this is, we have a slash here, sorry. So this should be negative 0.5. Okay, so anyway, here is the formulas to design the web for what? Unstiffened web. If the web is stiffened, so the formulas will be a little bit complicated. So this is the formulas for stiffened web. So for stiffened web, we have VB equal to alpha V, alpha D, alpha F, VW. So we will need to find 1, 2, 3 parameter, where alpha V is one of these values, alpha D is these values. But luckily, the standard give us another option to find alpha V and times alpha D in one step. So you will need to find this ratio here and using S over dB. S over dB is the stiffener spacing. So you can easily find alpha D, alpha V times alpha D. So actually what we will do for this formula, we will need to find alpha V times alpha D from this table. And we know alpha VW, sorry. So alpha F will be 1, can be taken as 1 or using this one here, this factor here. So for simplification, you can use alpha F as 1. So our efforts will be only to find the value of alpha V, alpha D from this table here. Okay? Do you have any question, guys, for this uh, part, for the lecture? I think we should stop here now because we have a class. Do you have any question, guys, for me? I just will not be able to go through everything in one lecture, so I just remind you with some parts of the hot rolled steel. Any question, guys? Michael and Yifan, all good? Okay. Thanks, guys. See you in the class. Thanks, Yifan.